Hello, today's paper unraveled is Trimmomatic, a flexible trimmer for Illumina sequence data. Published in 2014, the paper was authored by Bolger, Loesch, and Usadel. Trimmomatic is a flexible and an efficient tool that can process both single and paired end reads. Its pipeline-based architecture allows the user to define steps and the order of steps. Trimmomatic has multiple options on processing reads for trimming and filtering, but we will be looking into two main aspects mentioned in the paper. The first operation is removal of technical sequences. Technical sequences include adapter sequences and other user-defined sequences like list of k-mers, PCR primers, etc. There are two approaches to this operation: simple mode and palindrome mode. In simple mode, Trimmomatic works by finding an approximate match between the read and the technical sequence. Each read is scanned from the 5' end to the 3' end to see if any of the user-provided adapters are present using the standard seed and extend approach. The seed is not required to match perfectly, and a number of mismatches, as defined by the user, are tolerated. Based on a match, a local alignment is performed. If the alignment score exceeds the user-defined threshold, the tool removes the aligned region plus the remainder after the alignment. Testing proceeds by moving the contaminant towards the 3' end of the read. If there is a partial or a complete overlap at the 5' end, the entire read will be clipped. If the contaminant is found within the read, the matched portion and the rest till the 3' end are clipped. The testing process continues until only a partial alignment on the 3' end of the read remains. This mode, however, requires a substantial minimum overlap between the reads and the technical sequence to prevent any false positives. The downside would be its inability to detect short partial adapter sequence. So for such fragmented adapter sequences, one could make use of the second approach, which is the palindrome mode. It is specifically aimed at detecting this common adapter read-through where the sequence DNA fragment is shorter than the read length, resulting in adapter contamination. And this is how it works. The mode takes into account the fact that when a read-through occurs, both reads in the pair will have an equal number of valid bases, followed by contaminating sequences from the opposite adapters. Also, this valid sequence within the two reads, they will be reverse complements. So detecting all these three facts or symptoms, as the paper describes them, would result in identifying the adapter read-through much efficiently with high sensitivity and specificity. The alignment approach is similar to that of the seed and extend in simple mode. Global alignment scoring is used to end-to-end match across the entire overlap. The process begins with an overlap between the adapters and the start of the opposite reads. This alignment would check the read pair for useful sequence information. If there's no such information, which could be caused by direct ligation of adapters, Trimmomatic would drop off both the reads. If not, then the adapter proceeds to align or position the reads backwards. Even if there's only a small fragment of the adapter overlapping, the overall alignment is more than enough to detect adapter sequences. The process completes when the overlapping region no longer reaches into the adapters. The initial sequence comparisons are done using 16 base fragment from each sequence. These fragments are converted into the 64-bit integer seed using a 4-bit code for each base. After this, the seeds are compared using bitwise XOR. What it does is it determines which of the bits differ between the two seeds. If the bases match, the code is 4 zeros. And if it's a mismatch, say an AT mismatch, then the code is 0011. Ones are counted using the pop count operation, which will be exactly twice the number of differing bases for 16 base fragments. If the user has defined the distance and the seed falls within the range, then the full alignment scoring algorithm is used. Trimmomatic has two main quality filtering options. Both the methods use Illumina quality score, which you might find in a FASTQ file. So this score for each base is to determine whether or not to discard the 3' end of the read should the quality be low. With a typical Illumina data, one would generally expect to have poorer quality towards the 3' end. The two methods of quality filtering are sliding window quality filtering and maximum info quality filtering. The sliding window uses a relatively standard protocol for scanning low quality bases from the 5' end of the read and removes from the 3' end if the average quality of a group of bases drop below the specified threshold. This approach of grouping bases together and taking the average prevents a single weak base causing the tool to remove subsequent high quality data. The second method is quite a novel approach. According to the authors, this was created because for many applications, short reads are almost worthless because they occur multiple times within the target sequence and therefore give very vague and misleading information. Even though there is a risk of introducing errors because of retaining low quality bases in a read, it would be sufficiently long enough to be informative. However, too much retention of additional bases is like the short reads, less beneficial and more detrimental. So we can conclude that reads of moderate length can almost be as valuable as full-length reads. Like mentioned earlier, the quality of reads drops significantly towards the 3' end. So we could benefit much from a trimming process that becomes increasingly strict as it progresses through the read rather than having a fixed quality threshold. This progressive quality filtering is a novel method, according to the authors. The maximum information quality filtering approach implements this adaptive approach. It uses a combination of 3 factors to determine how much of the read should be retained. The first factor models the length threshold concept, where a read should be of and above a minimal length for it to be useful in the downstream application. I mentioned how very short reads are too ambiguous to be informative. We also have the other extreme, the long reads that cannot be uniquely mapped to locations in the target sequence because of them originating in a repetitive region. It is unlikely that a small number of additional bases will resolve this. For reads between these extremes, additional bases could be the difference between an ambiguous and an informative read. A logistic curve is used to score this behavior because it gives a relatively flat score for extreme values and a steep transition around the user-specified threshold point. The second factor models coverage and provides a linear score based on retained sequence length. So a longer read with high accuracy bases contains more information that is useful for applications. The final factor models the error rate and uses the error probabilities from the quality scores to see the likelihood of errors accumulated over the read. The product of the probabilities that each base is correct gives us the score. A user-specified strictness setting, S, can be set between 0 and 1, and this balances the coverage factor and the error rate factor. So putting together all these factors gives us the overall formula. Thank you for watching. If you found this video helpful, please do consider subscribing and sharing it with your friends and colleagues. And do let me know your comments and thoughts. The email address is linked in the description box. Until next time, happy researching.